pleasure to be here back at this seminar that was started by Eli Goodman and Ricky Pollak many years ago. And it is a coincidence that today is Eli Goodman's birthday. Unfortunately, more than a year ago. And for those who didn't know him, this is Eli, I think in 1999 in Ascona, Switzerland. And he was really sunburned. It's not just a bad quality picture. And I wanted to show check it. I wanted to show another picture of Ricky and Eli from 1986, I guess. Talking boys are from Hungary. That was during that first visit in Hungary. And so the title of my talk is Perfection and Crossing, and perfection, it has something to do with perfectness, perfect graphs, and the person who introduced this notion, this concept is Claude Berge, here talking to POLYNOMIALLY in Marseille at a conference, and both of these individuals played a very important role in most of the questions that I will be speaking about. So let's start at the very beginning. So the definition of perfectness, but we need two familiar notions for that. One of that is the chromatic number of the graph, and the other is the clique number. So the clique number is very easy. It is just the maximum number of vertices you can find in the graph, so that any two of them are connected by an edge. That's a clique. And the chromatic number is the minimum number of colors you need to color the vertices, so that no two vertices that receive the same color are connected by an edge. And obviously, this is a relationship between the chromatic number and clique number. You need at least as many colors as the clique number, because for each vertex of the clique, you need a different color. And you may hope, if you are totally innocent, that these two numbers are actually equal in most cases, but they are very much not equal. And this was realized at an early stage of the development of graph theory. So there are several constructions, and I listed them because I will refer, I guess, two of these constructions later, and I will also outline them. Perhaps the most interesting part of it is that they are very much not equal. Not only it is not true that, so what is a triangle-free graph? A graph is triangle-free if it has no triangles. So this means that no clique of size 3. So it is possible that the clique number is 2, no clique of size 3, but the chromatic number is arbitrarily large. And this is not only, this is the case, but it comes from beautiful probabilistic proof of POLYNOMIALLY 1959, that actually there are graphs that not only don't contain a triangle, but don't contain any short cycle, shorter than whatever, 1 million, your favorite number. And yet their chromatic numbers are arbitrarily Now,
but is it a very special construction, or what happens in sort of the random graph case?
this is you have to be a little bit clever to kill the short cycles, but it is essentially this construction can be derived from a random graph, but then you have to kill the short cycle. And we know that these two parameters, the chromatic number and the clique number, they are extremely difficult to determine. I don't want to sort of go into that. I only indicate that computing them is an NP-complete NPR problem, and in fact, even to estimate that these parameters is a difficult task. So, returning to these definitions, still there are some cases when these two numbers are the same. They are very special graphs. This is what Claude Verge called perfect graphs, those graphs for which the chromatic number is equal to the clique number. Moreover, this is true for every induced subgraph of the graph. So these graphs are perfect graphs. And somehow, at an early stage of graph theory, people really paid a lot of attention to perfect graphs. It was studied, and there were two. So the most important, perhaps the first interesting example of perfect graphs was this geometric. You can call it geometric example. This was proved by Galai and János, that if you define a graph in the following way, that you take intervals along a line and you assign to each interval a vertex, and you connect two of them, like 1 and 2, by an edge, if and only if the two intervals overlap, intersect, then what you get is the intersection graph of the system of segments. And intersection graph of a system of segments, this is always a perfect. For them, the chromatic number is equal to the clique number. There are many beautiful simple proofs of that. So you may hope that it easily generalizes to higher dimensions. So for instance, in the plane, you can take, instead of intervals, axis parallel rectangles, and you look at their intersection graph. But as this example shows, the intersection graph of this system is a cycle of length 5, in which there is no triangle, meaning that the clique number is 2, and yet the chromatic number is equal to 3. So definitely, these are not perfect. But there are several graphs that are perfect graphs. I don't want to define them. Famous big classes, comparability, incomparability graphs, chordal graphs, and so on. And there is a big chunk of graph theory which is sort of involved in a number of interesting minimax theorems, to some extent related to linear programming, for which you really get this perfectness, and some by minimax theorems, because the chromatic number is the minimum number of colors, the clique number is the maximum size of a clique. And there are many such theorems in which the minimum of something happens to be the maximum of something. Okay. So the first, so Berge had two interesting conjectures about perfect graphs. The first one is the weak perfect graph conjecture. So this says that a graph is perfect if and only if its complement is perfect. This is a highly non-trivial statement, and in fact, a celebrated early result of Lovaas from 50 years ago. But Berger also had a stronger conjecture, actually a complete characterization of perfect graphs. So it said that a graph is perfect if and only if neither the graph nor its complement has an induced cycle, an induced odd cycle, bigger than a triangle. So what is this? Induced odd cycle? It means that you have it doesn't matter. Also, for those who don't see that, or you can show it when you have to show. So here is your graph G. So what is an induced subgraph? An induced subgraph, it just means that you take a subset of the vertices and all edges of the graph which are between these vertices. So you cannot leave out anything. This is the induced. So such a thing, for instance, a used pentagon, so that there are no other edges, it cannot exist in the graph and no odd side. This is fine because it's not an induced. So this was the strong perfect graph conjecture. Of course, by the definition of the this thing, you see that it's symmetric with respect to taking complements, and this is in fact reflected by the weak perfect. So it took actually 30 more years for Chudnovsky, Robertson, Seymour, and Thomas to prove the strong perfect graph theorem, but now we know that. And in fact, shortly after that, you won't be surprised, they also managed to prove that it is computationally not very difficult to determine that a graph is perfect. This is based, of course, on the characterization.
All very surprising.
Wait, is there some problem? I mean, what happens if you have a complete graph on 4 vertices? That doesn't seem like it. Isn't that perfect?
No, because so where do you find? Oh, you mean that if the number of vertices is smaller than
5? I mean, if you have a complete perfect graph on 4 vertices, the chromatic number and the the 4.
Yeah,
right? But it doesn't have a cycle of length 5, 7, 9.
If you that's true. So I guess that you have to assume that the number of vertices is at least 5. At least 5. Yes. Yeah. So now this is a picture of János and Lehel. Maybe his birthday or something like that. So these are 2 people who introduced a very interesting modification of this question. So, okay, most graphs are not perfect, but perhaps many of them are nearly perfect. So what does it mean that they are nearly perfect? So for perfect graphs, the chromatic number and the clique number they are equal. But for near, so they introduced the notion of a chi-bounded graph. So it's a class of graphs is chi-bounded, and they are not necessarily equal, these 2 numbers, but at least there is a relationship between them. So this means that in the class of graphs, I call them chi-bounded, nearly perfect, if at least there is a function so that the chromatic number is bounded from above by this function of the clique number. So in general, this is not the case because we have seen graphs for which the clique number was 2 and the chromatic number was arbitrarily large. But in many cases, there are such ones. And interestingly, those examples that were found for chi-bounded nearly perfect classes of graphs, they were geometrically defined, most of them. So here, the first example is the example that I showed you, this axis, the intersection graph of axis parallel rectangles, right? Well, they are not necessarily perfect, but Asplund and Grünbaum in 1960, and perhaps that was the first result much before this concept of chi-bounded or nearly perfect graphs was introduced. They proved that intersection graphs of rectangles are chi-bounded. So what they proved was more precisely that chi is at most big O of omega squared. But it doesn't matter. It's important only that it is bounded by a function of omega. If it were bounded by 2 to the 2 to the omega, it would be fine. Of course, it's a weaker result, but then according to this definition, they are also nearly perfect. And then the same is true for intersection graphs of both in any dimension, or if you look at instead of intersection graphs, you look at disjointness graphs. Disjointness graph is that, again, disjointness graph of balls. To each ball, you assign a vertex, and now you connect them not when they have a point in common, but when they are disjoint. So the complement. Disjointness graph, the complement of intersection. And disjointness graph segments, Törőcsik was at that time PhD student at Koran. You definitely remembers him, that they are also nearly perfect. So, what is this? Who can see this transcript? Cool. So, for intersection graphs of axis parallel boxes in the plane, so this is this example that I told you before, where Grünbaum and Asplund proved this bound. Actually, there is a better bound now, after many years, Chalem-Stock and Walchuk improved this omega squared to omega log omega. A big improvement. You look at the complement of it for disjointness graph, complements of intersection graphs of same axis parallel boxes in the plane. Now we know that again a similar phenomenon is true. In fact, with this next to this omega is a better function. Instead of log omega, there is log omega. So this is for disjointness graphs. So for disjointness graph, omega means the largest clique, but the largest clique in the disjointness graph is really a set of disjoint objects. Right? Okay. Interestingly, in both cases, the conjecture is, well, I am not sure if it is the conjecture. Most people believe that. That's what I can say, but I'm not sure that if it was explicitly stated as a conjecture, that in fact this overhead, this logarithmic or log overhead is not needed. I think that this is really an important open problem in the area to decide whether for these graphs the chromatic number is really just a constant times the peak number, which really means that they are nearly perfect. So it very often happens that there are these parallel results for intersection graphs and disjointness graphs of certain objects. It's not an isolated case. So it wasn't an entirely silly conjecture by János in 1985 that perhaps it is true that if you take two families of intersection graphs, of families of disjointness graphs, of a class of geometric objects, or even, two complementary classes of graphs. One class is chi-bounded, perhaps, if and only the other class, the complements are chi-bounded.
And that's true even for unbounded objects. So yeah, I mean, we've seen this for segments and for rectangles, but it's never been like one-sided.
Yeah. There are many examples, straight lines and unbounded objects.
Too. Okay.
Yeah. And also non-geometric objects. So here is, let me show you one example where we compare intersection graphs and disjointness. So in 1994, we proved that if you look at disjointness graphs of segments in the plane, then they are chi-bounded. In fact, the proof also gave that the same result is true not only for disjointness graphs of segments, but for disjointness graph of any X monotone curves. So what is an X monotone curve? Like this. It's like a curve so that every vertical line intersects it at most one point. Connected curve. Of course, if you have a segment, in general position, forget about the vertical segments, that they are X. And it turned out that years later, actually, many years later, 20 years later, surprisingly, that this bound is tight for X monotone curves. But we still don't know if it is tight for segments. Simply, perhaps there is a much better result for segments. Definitely, it is not true that chi is bounded from above just by constant times omega, but maybe it can be bounded from above by a quadratic function of omega, and I think it's an interesting and not hopeless answer. Now look at the complement. And this was a really big surprise 70 years ago. Proved by a number of undergraduate and graduate students in Poland, together with honorary graduate student Tom Trotter from the US, that actually for intersection graphs of the intersection graphs of segments in the plane are not chi-bound. In fact, there are triangle-free intersection graphs. This means omega is equal to 2, for which the chromatic number is arbitrarily high. We don't know here. The hope is that perhaps one of these logs can be removed. That's another interesting special case, which shows that it is not true that this conjecture of János was not true. There are classes of graphs whose are chi-bounded and their complements are not chi-bounded. nevertheless, it was a very fruitful conjecture, which really sort of motivated a lot of research in this area. So the question arises that how can we decide about a family of graphs, whether it is chi-bounded or not chi-bounded? So here we have seen that the intersection graphs of segments are not chi-bounded, but here is a theorem, János and Leher, 1985. If we look only at segments that are chords of a circle or any convex set, like on this picture, then they are chi-bounded. It's very close, right? It's not just we are restricting that. We are not looking at all segments, intersection graphs of any kind of segments, only chords of a circle. And now this was a big improvement last year that Jim Davis proved that actually the bound is omega log omega, and we are even close to determining the best constant. The construction, the lower bound construction, which shows that examples of graphs for which a chromatic number is at least omega log omega. Omega is a big number. Was already given by Kostashka in 1988. It was a paper which for a while was a mystery for the Western world because it was written in Russian. But then you see Russians move to the United States and everybody learned Russian or they learned English. And now everybody knows this. Now I'm showing you another conjecture about this subject, which was given by Esprit, habilitation. What is habilitation in France? Sylvain, you must know.
No what, sorry?
What is a habilitation schrift in France?
Well,
Some thesis, some
thesis d'état, I think, no?
thesis d'état. So he had this conjecture. Actually, he had two conjectures. Another very influential conjecture.
More precisely, thèse d'état.
What is a hereditary class?
Hmm?
What is a hereditary class of graphs?
Yeah. So I will first I read it and then I explain it. So hereditary class of graphs is chi-bounded only if and only if there is a constant so that the chromatic number of the graph is at most this constant for every triangle-free member of the family. Now this hereditary, it's not a very good expression, but what it means is, what it means is just that actually, this is the drawing that I wanted to make, so I don't know why I arranged it. So in a hereditary class, if you have a graph and you have a subset of the vertices, then the subgraph induced by this vertices also belongs to the class. This is hereditary. So whenever a graph belongs to the class, then the induced subgraph of it also belongs to the class. So all of these examples, like intersection graphs of segments, right? Or intersection graphs of anything. Of course, they are hereditary classes. Or if you look at the class of graphs that don't contain a triangle. The graph doesn't contain a triangle, the subgraph doesn't contain a triangle. They are all hereditary classes.
But János, am I correct? There's no geometry in this conjecture. I mean,
no.
Any kind of
Yeah.
class. So it could
This
be
is
abstract.
This is a very, very important point to which remind me I will return.
Okay.
Yes, no, it's a very general conjecture. Therefore, it is really a beautiful conjecture. So I just want to say that if this conjecture is true, then there are lots of nice things that we can prove with it. So here is an example. So again, what does it mean? It means that for this hereditary class of graphs, chi-bounded would mean that chi, the chromatic number, is bounded whenever the clique number is bounded. And it says that we only have to check it for clique number 2 for triangular tree graphs. And if it's true for clique number 2, it's true for clique number 3, 4, 5, and so on. So here is a celebrated theorem of Scott and Seymour, which is motivated by the perfect graph theorem, the strong perfect graph theorem, says that if I look at the class of graphs that don't have an induced cycle of lengths 5, 7, 9, odd lengths, this is 1/2 of the strong perfect graph theorem, because the strong perfect graph theorem talks about graphs which don't contain an induced cycle of this kind and neither do their complement. So then this class is chi-bounded. Now assume that this conjecture is true. Then it is enough to check whether it is chi-bounded for triangle-free members of the family. But if I look at the triangle-free members of the family, it doesn't contain a triangle, doesn't contain a cycle of length 5, 7, 9, doesn't contain any odd cycles. But if it doesn't contain any odd cycle, then it is a bipartite graph. If it is a bipartite graph, then its chromatic number is 2. That's why it's bipartite. It can be followed by 2 colors. So this would be an immediate consequence of this conjecture. But unfortunately, after I give away the punchline, this is unfortunately not the case. And here so let me outline the proof, because the proof is really beautiful, and it starts with one of the most elegant examples of a triangle-free graph whose chromatic number is large. This is Vyckoff's construction from 1949. So we define by recursion or induction, if you wish, a series of graphs, Gn, so that their chromatic number is n, and they contain no triangle. Okay? So assume that we have already defined an n-1 chromatic graph, Gn-1, which is triangle-free. Then we take n-1 copies of this graph, disjoint copies. Now the chromatic number of this graph is n-1. It means that if we color it with n-1 colors, then we have at least one vertex of each color, right? Otherwise, it would be n-2 chromatic. So chromatic number would be n-2. Okay. So we take these n-1 copies of this graph, and we pick one vertex from each of these parts in all possible ways, and we assign a vertex to that which is connected to this n-1. So we pick in all possible ways one vertex of each, and we have. Obviously, we didn't create a triangle. Previously, there was no triangle. After that, there is no triangle. Now, there is also...
Okay, I just have a question. So for each choice of a point of a vertex from each of those sets or graphs, we pick a different
vertex. Vertex. Absolutely. So that's very important. So there is a large number of vertices. This is a disadvantage, but okay. And although I orient all of the edges from left to right just for fun, they have no relevance as for the chromatic number of the graph, but let me orient them from left to right. And then we get a directed graph, and this directed graph has the property that between any two vertices, like this vertex and this vertex, there is only one directed path connecting them. Because, you know, if from here, for instance, I can go to here, then I must go through this vertex. And so if here, between this and this, there was only a unique oriented path, then this property will be preserved. Okay. And now I do something silly, and this is what will disprove the previous conjecture of Asprey. I will look at this graph, and I will add some edges to this graph. It will be
the fact that there's less than or equal to one path is because that set was triangle free, right? Otherwise, there would have been two. There could have been two.
Because no, it is because originally there was at most one. So there is no directed path between these two vertices in different parts. And then by induction, this property is preserved because I picked only one vertex from each path. So originally there was at most one such path. And after I added this vertex couldn't have created two paths between, I mean, one vertex here and this vertex, because all of those paths should have gone through this x1, but between any other vertex and x1, there was only, by recursion, there was only one directed path. So this property is just preserved by it. Okay, so what we do now, we look at this graph GL, which we define in this way recursively, and we add some edges to that. We add some edges to that, then it will become a graph GM star, a bigger graph. If it is bigger, then its chromatic number can only grow. The number of colors we need can only be larger, okay? And we do it in such a way that if you look at a triangle-free subgraph of this new graph, then its chromatic number will be at most 4. That will be a contradiction, because then it would mean that we found graphs whose chromatic numbers are arbitrarily large, but for triangle-free induced subgraphs, it's always induced. So I tell you how we do that. This is not my proof, but not written here. It's Sophie Spirkel and co-authors. Beautiful construction, which was since then. I think on the next slide we will see their names. So they do the following: that we look at this graph and we add some edges to that. If we find two vertices, as I said, there is a unique path between them if they are connected by a directed path. If the length of that unique path is congruent to 1 modulo 3, looks arbitrary, this congruence and things like that, then we add a black edge between them in this direction. So in particular, you know, if you look at these green edges, x2 and x are connected, the shortest path between them consists of one edge. its length is 1 modulo 3, because 1 is congruent to 1. Therefore, it will be black. So all edges that are originally in the picture will be black, but there will be some additional black edge. And if the length is congruent to 2 modulo 3, then we add the red edge, but we add the red edge not from X to Y, but in the other direction, in the opposite direction. So now we have black edges and red edges, and there is a very simple, and this is our graph. This is our graph GN star, which is bigger than the original graph. And you know, if you have 2 consecutive black edges, this means that this length is congruent to 1, this length is congruent to 1, then this means that from here to here, the length is congruent to 2. So we add a red edge in the opposite direction. And similarly, if you have 2 red edges oriented in this way, then we have a black edge. So there are black and red edges, and what we don't have, as is shown by this example, 2 consecutive edges, so that in the same direction there is a third edge. This is transitive. The cycles we have, but we don't have. And because we don't have this, if I look at a triangle-free subgraph of this graph, then it cannot happen that then all the incoming edges must be of one color, and all the outgoing edges must be of. So it cannot happen that at a point there is an incoming black edge and also an outgoing black edge. Because if there's an incoming black edge and there is an outgoing black edge, then because of this picture, there should be a third edge connecting them, but it's a triangle-free subgraph. There is no third edge. So this means that the incoming edges are there is no incoming edge and outgoing edge that have the same colors. So this means that every vertex is either black and red incoming edges or black incoming edges and red incoming edges. There are 4 possibilities. And it's very easy to see that if you color the vertices of this graph according to these 4 possibilities, then it is a good coloring. The chromatic number is 4. That's right. This conjecture of Asprey was incorrect, but now I return to Joel's question. So forget about it. So this means that it is not true that for checking whether a class of graph is chi-bounded, it is enough to check all of the triangle-free subgraphs. It's not. Yet it is possible that it is true for geometric examples. The example that I constructed was very much combinatorial from Zhikov's example, and from this example. So we really don't have any class of intersection graphs or disjointness graphs or other geometrically defined natural quote-unquote classes for which Asprey's conjecture wouldn't be true. So it is, my hunch is that it is true, just one has to determine the right range of graphs for which we apply. So here is another interesting conjecture. Yeah, I am aware of the time. I try to be quick. It's a.
I think you can have another 10 minutes.
Okay. So what is the exactly on Zoom? You know, anyone can just go to the kitchen. So but I don't want to take advantage of it. So a family of graphs is polynomially chi-bounded, obvious definition, if it is true that the chromatic number is bounded by a function of the clique number, and the bound is a polynomial. And a beautiful conjecture of Esprit, other conjecture is that if a hereditary family, again, for this whole problem to make sure, we have to assume that if a graph is in the class, then its subgraphs are also in the class. So if it is chi-bounded, then it is polynomial. Of course, this K can be arbitrarily large, but polynomial. Another very fruitful conjecture, and unfortunately, shortly after the previous paper by Spirkel and company was published, it was the same method, same construction, very similar one was applied by Bryansky, Davis, and Walchuk to prove that for every function, there is a hereditary family of graphs for which the chromatic number is at least f of omega. So this is very much not true. But again, the same weakness as was pointed out by Joel, the construction is again for abstract graphs and for geometric examples. My hunch would be that that there is a positive. Now, I'd like to point out that this whole subject of chi-bounded or nearly perfect graphs is very much related to one of the central topics of graph theory. This is Ramsey theory. So again, the clique number we have seen, and the independence number is the complement, the largest number of vertices in the graph, so that no two of them are connected by an edge. And what Ramsey's theorem says, in this quantitative form proved by János and Szekeres 87 years ago, is that every graph with n vertices contains either a clique or an independent set of size log n. So one of these two n is the number of vertices. One of these two parameters must be large, log n. At least log n, and this cannot be improved. So the question is, can it be improved? So I just said that no, it cannot be improved. Actually, random graphs show that there are many graphs of n vertices for which we cannot find either a clique, in fact, Morse graphs, either a clique or an independent set of size bigger than log n. But perhaps for many classes of graphs, it can be improved. And the famous conjecture of János and Pach, which they probably had already at this time when the picture was taken in 1971. Yes, this guy is more than 50 years old now. Is the following. So if you have a hereditary family of graphs, then actually there exists a constant so that either the clique number or the independence number is larger than n to the depth positive constant. This n to the c, maybe c is a very small number, like 0.0001. Nevertheless, if n is large, it's much bigger than log n. which was given in by Ramsey's theorem. So this would be a huge improvement. Now, in fact, János and Pach did much more than that, because they really proved that here is, in this case, we can put something bigger than log n, namely e to the square root log n. But e to the square root log n is infinitely larger than log n, but infinitely smaller than n to the constant. So that they proved. So they proved a better result. Definitely there is a positive result, but is this true? Now, in the last few years, there were a lot of efforts to prove this conjecture by several groups. And for large classes of graphs, for instance, I don't want to define them, semi-algebraic graphs, including intersection graphs of segments, lines, circles, whatever, it follows from a general theorem of Alon and company for graphs that don't contain a cycle of length 5. This was an upsetting open case for a long time, and János and Pach thought that if one could decide this question for this class, then everything else would follow in general. Well, Chudnovsky, Scott, Seymour and his team actually proved this special case, but it doesn't seem to solve the general problem. There was another interesting breakthrough by István Tomon for string graphs. Let me define that. So there is one thing that is very easy to check, that if a class of graph is polynomially chi-bounded, like there is a bound for chi, which is a polynomial of the big number, then they satisfy the ambition. But in general, the conjecture is open, and today we can't even tell. I mean, maybe it's open because it is just wrong. Now, I don't want to show you any more slides. I just want to finish with one open question, which is in the very peculiar question, but to some extent, this is the only open question in an area of problems related to chi-boundedness, and I think that any high school student is in as good of a position to solve this question as I am, perhaps an even better position, because you are better problem solvers. So if you look at disjointness graphs of strings, so what is a string? A string is just a number. It is actually not necessarily this is a string. And so we have a bunch of strings in the plane, and we look at their disjointness. This is a class of it. So it turns out that it's not trivial that disjointness graphs of strings are not chi-bounded, not nearly perfect. In fact, so I have written a paper with Gábor Tardos and G is a tool, in which we prove that not only disjointness graphs of strings are not chi-bounded, but if instead of strings, we consider disjointness graphs of just simple strings that consist of two segments. And we can call them letter V's, right? So if we have a bunch of such objects, that disjointness graph, so this means that we assign a vertex to each of these things. Two of them are connected if they are disjoint. This class of graph is already not chi-bounded. So what is the question? So the question, and for segments, we know if instead of this, we only look at segments, they are chi-bounded. So what is the question? The question is that if we look at disjointness graphs of segments, let me write it here. So disjointness graphs of are disjointness graphs of letters V. Now you understand what it means, right? Any pair of which intersect at most once. It looks like a little detail, you know, so here this is not allowed because if you look at these two letter V's, they have 3 intersections, right? So even if I stopped here, it wouldn't be allowed because they have 2 intersections. So this is the problem. You know, if my conjecture would be yes, but you see that there have been so many. I showed you 3 conjectures in this one lecture, which are all beautiful conjectures turned out to be false, or at least false in the way how they were posed. So who knows? Maybe you can come up with a construction of letter V's so that any 2 of them intersect only at most once, but that disjointness graph has large chromatic number. And so almost all of those names you see here are people who would be interested in such a thing. So this is a good point to stop at, and I'd like to thank you for your attention, and I am honored that so many people showed up in person, and I am happy to speak in front of real people rather than in front of artificial computers.
Axis parallel rectangles?
Yes, like in front of axis parallel rectangles, exactly.